Hello and welcome. In this module we will look at reflection of uniform plane waves upon a boundary, and then we will talk about the phenomenon of total internal reflection. Okay. So, when a wave propagates because of some reason you have generated an electromagnetic wave, it is propagating along a certain direction and in a particular region which we will assume it to be uniform, linear and isotropic, okay, which is characterized by the three material properties mu1, epsilon1 and sigma 1. So, this wave is propagating happily. Now, it hits a boundary. Okay. So, the wave hits a boundary because beyond this boundary there is mu2, epsilon2 and sigma 2. You can expect that the electric field and magnetic field here of the wave will be different from the electric field and the magnetic field here. Okay. You might remember actually, if you think that electromagnetic wave, light is an electromagnetic wave, that when light strikes one medium, there are two important things that will happen. Okay. Assuming that the medium is nice, flat and everything. Okay. When a ray of light hits that medium, there will be one component of the light which is reflected. Okay. So, there will be reflection phenomenon, and a portion of the light goes through the second medium, which is called as the refraction, right. So, a portion of the light goes inside, this phenomenon is called as refraction. Okay. So, when a wave hits a boundary, you get reflection and you get refraction. You have probably also studied certain relationships between this reflection and refraction, right. So, you must have studied the statement that angle of incidence is equal to angle of reflection, or rather angle of reflection is equal to angle of incidence, and to find out the angle of refraction you must have used what is called as Snell's law. So, you have the first Snell's law which tells you that angle of incidence is equal to angle of reflection, then the relationship between angle of transmission and the angle of incidence is related normally in terms of the refractive index of the first medium and the refractive index of the second medium. This is something that you know. Let us look at where those laws are coming from. They actually are nothing but matching conditions, boundary matching conditions, as we will demonstrate now. In understanding the reflection of the waves, okay, we have to define first certain quantities. I will imagine that this my hand is the surface and this is the direction in which the incident electromagnetic wave has hit the boundary. Okay. To this my hand, which is the surface which separates the two medium, I can find what is the normal to the surface. Okay. The normal being perpendicular to the surface. So, in this particular case the normal is along this direction. Okay. So, you have a wave which has come in and then there is a normal here. So, there is an angle between the direction in which the wave has come and the normal. So, if you think of this point as O, this point as A, this is hitting here. OA line represents the direction of the incoming wave, and if I consider for this perpendicular line this as N, then AN represents the normal to that particular point. Okay. And the angle between OA and AN is the angle of incidence. Clearly, when the wave is reflected, it is going along this particular direction, okay, and compared to this the direction of the wave which is reflected and the normal, there is an angle of reflection. Below here I have wave which is transmitted into the second region. Again I have a normal and an angle to the normal, giving you the angle of transmission or angle of refraction. Okay. So, there are these three angles. This hand of mine which determines the boundary, right, is described by two vectors, two tangential vectors. There is one T1 here and a T2 vector. This T1 and T2 define a plane which is defining my surface or the boundary. Okay. These are tangential to the surface obviously. So, these are tangential. Look at this hand, this is one direction, and my thumb, so this is one more. So, these two which are perpendicular to each other are defining this plane, and this is the plane of interface. Okay. Similarly, I can actually have a plane which is described by the incident k vector and the normal to the k vector, or rather I can have, because this can be decomposed into one of the tangential components, right. So, we call this as T1, remember this as T1 and this thumb as T2. So, when I look at a wave which is incident in this way, I can decompose this into one component along T1 and one component along normal. So, this normal and this angle T1, they will create one plane which is called as the plane of incidence. Okay. So, you have a plane of incidence and a plane of interface. We have only talked about the direction of the wave. What about the direction of the electric and magnetic fields? Well, the electric field can be perpendicular and lying in the same plane, that is electric field can lie in the plane of incidence, but the magnetic field will be lying in the perpendicular scenario, right. So, the magnetic field can be perpendicular, that is it will be along this thumb for example, or you can have the magnetic field lie in the plane of incidence perpendicular to the line OA. However, the electric field line in that particular case must be perpendicular, because we are assuming E, H and K are perpendicular to each other. This is the plane wave condition that we are assuming. So, this is the direction of K, this is the electric field which is in the plane of incidence and the magnetic field which is perpendicular. Such a situation is called as parallel polarization for very obvious reason. It is parallel polarization because electric field is in the plane of incidence. If it is the magnetic field which is in the plane of incidence, so this is the K vector, this is the magnetic field and the electric field was perpendicular to you, then this is called as perpendicular polarization or transverse electric polarization, and that is the case that we will consider in this particular module. The case for TM wave is very similar to the case of TE wave, and I will leave that as an exercise for you to fill in. Okay. So, we have the TE case, right, which you can see from this figure. The wave is propagating in the x z plane. Okay. This incident wave has a direction which is given by this k vector given in the red color. Okay. So, this gives you the incident wave vector. So, this is the incident and the electric field is assumed to be along the y direction, indicating that it is perpendicular to the plane of incidence. Plane of incidence is formed by this red color line and the black color line, okay, which is the z axis. Z axis and the red axis form the plane of incidence. The plane of reflection is formed by the reflected light, which is indicated along this or propagating at an angle of theta r with respect to the normal. The normal is along the z axis. Okay. So, this point is z equal to 0, obviously the interface which is separating the two media. The second media has constants mu2, epsilon 2 and sigma 2. There is also plane of transmittance which is equal to plane of incidence, because the k vector making an angle theta t will still lie in the same plane of incidence. In fact, you can see that all these planes are equal, that is plane of incidence is equal to plane of reflectance, plane of reflection and plane of transmission. All these three are the same planes. Look at the orientation of the magnetic field lines, which are shown by the directions in blue color. Okay. So, for the incident wave, the magnetic field is directed in this particular direction, reflected wave it is directed here, and this is the direction for the transmitted wave. Does it make sense? Yes. So, you have to now think that the electric field is perpendicular and coming to you. So, this cross H will be going along the k direction. If the magnetic field is in this way, electric field is in the top. So, this cross H will give you a wave which is propagating this way, that is a reflected wave, and for the transmitted it is the same thing. This is the electric field, this is the direction of the magnetic field. So, crossing like this will give you the direction of the wave which is transmitted. Okay. These are the different ways in which these waves are transmitted. Now, what we want to write down is the expression for the incident wave vector, the reflected wave vector and the transmitted wave vector or the propagation constant k, right. What would be this k I for the incident wave? This is making a certain angle theta I. So, there will be a component along plus z and plus x, correct. This is given by cos theta I z hat plus sin theta I x hat, whereas for the reflected wave, because it has to propagate along minus z direction, this will be minus cos theta r z hat plus sin theta r x hat. For transmission, it is cos theta t z hat plus sin theta t x hat. It is these e to the power minus j k I dot r, e to the power minus j k r dot r, e to the power minus j k t dot r, which describes the phase components for the incident, reflected and transmitted waves. That is, incident wave will be described by the electric field E incidence and this phase factor. This is the reflected wave, so it is E ref into this one, and this is the transmitted wave, which is transmitted times e to the power minus j k t dot r. So these are the phase factors that we have to attach to the plane waves. Okay. What can we write about Hi? Well, Hi will have one component along minus x direction and one component along x direction, correct. So the magnetic field will be given as minus x hat cos theta I, because there will be an angle of 90 minus theta, plus z hat sin theta I. Okay. This would be the direction of the magnetic field. If Ei is the amplitude of the incident electric field, or the wave has an amplitude of Ei, then Ei by eta 1 will give you the amplitude of this magnetic field, right. And there is e to the power minus j k I dot r, which is coming from this particular expression. Okay. And similarly, you will have Hr given by x hat cos theta I, you can see the angles from the figure, z hat sin theta r, E r divided by eta 1 e to the power minus j k r dot r. Okay, this is the reflected electric field. Similarly, Ht will be given as minus x hat cos theta t plus z hat sin theta t E t by eta 2 now, not eta 1, it is eta 2 e to the power minus j k t dot r. Okay. What would be the electric fields? Electric fields are all directed along y axis. Incident field has an amplitude Ei, reflected field has an amplitude of Er, transmitted field has an amplitude of Et. Okay. All of them are directed along the y axis, and each of them will carry this particular phase factor. Okay. So this is the list of electric field components, magnetic field components, and the k vectors that we were requiring. Now what do you have to do? Well, you first break up the incident vector into its tangential and normal components, right. So when you break up this into tangential and normal component, you will see that the tangential component is actually the x component, correct, or rather the minus x component in this case. If you break up this into tangential or decompose it into tangential and normal component, you will see that it is only the x component which is tangential to this boundary, because anything that is along z will be along normal, correct. Finally, if you decompose this into normal and tangential, again you will see that only the x component, or rather minus x component, that is tangential. Okay. Where are we applying the boundary? We are applying the boundary at z equal to 0, and we want to know only the x components of the H fields. What about the E components, that is electric field components? They are all lying along y, y and y, and y is a tangential component for the surface, correct. Z equal to 0 has a component of x and y, sorry, the axis x and y. So any field which is directed along y will be tangential to that. Therefore, all these three are tangential. Now you remember what we talked about in the boundary condition. We said that tangential E must be continuous. Tangential E1, or rather tangential components in region 1 must be equal to tangential components in region 2. So Et1 equals to Et2. However, what is the total tangential component in region 1? It is the sum of incident and reflected electric fields, correct, because both are in the same region. So you actually have to write this as Ei plus Er is equal to Et. Is that correct? Have we written it correctly? Well, there is a small catch here. I will tell you what the catch is. This equation as we have written is wrong, because we forgot the phase factors. Let us put down the phase factor here. So this equation actually has to be written as Ei e to the power minus j. Now let us look at what happens to the phase factor when I consider the position vector r as x hat plus y hat plus 0 into z hat. You might question why a 0. Well, the answer is obvious, because we are assuming that this interface is given by z equal to 0. And is there a component of the k vector along y? No. So, these components, these two will not be useful for us. The only tangential component or the phase component that you are going to get will be along the x direction, and this phase that you get is given by, for the incident wave, this is given by sin theta I into x. For the reflected field, you will get sin theta r into x, for the transmitted you will get sin theta t into x. Okay. So, let us carry these phase factors along with EI, ER and ET. So, let us write this as EI and write the phase factor here, e power minus j x sin theta I plus ER e power minus j, the phase factor is x sin theta r, there is a k here which I forgot to put, right. So, there is k here and this k has to be ki, kr and kt. So, there is actually ki, kr. Did I forget to put ki here? Oh yeah, here I forgot to put ki here. This has to be multiplied by the magnitude of k, which is ki for the incident vector, kr for the reflected and kt for the transmitted wave vector. Okay. Sorry, I forgot to put that. Now, you can go back and put those equations. This must be equal to the electric field tangential component on the other region, which is Et e to the power minus j, the phase factor is kt x sin theta t. In contrast to the boundary condition that we derived in the last module, here you have to satisfy the boundary conditions for all points along x, right. So, it is not just at one point that you have to satisfy, you have to satisfy this at all points along x. So, the only way you can satisfy them at all points along x is if you ask ki sin theta I be equal to kr sin theta r, which must be equal to kt sin theta t. Okay. So, this has to be equal to, each of those terms, phase terms have to be equal to each other, so that no matter what the amplitudes EI, ER and ET are, this equation has to be valid, the boundary condition has to be valid. Okay. So, in order to make this boundary condition equal for all values of x, for all values of EI, ER and ET, this should be equal. However, ki is nothing but omega by Vp1, which is the phase velocity in medium 1, sin theta I is equal to omega by, what is the phase velocity for the reflected wave? It is the same as the incident wave, correct. So, you have omega by Vp1 sin theta r, which must be equal to omega by Vp2 sin theta t. Now, take the first two equations. In the first two equations, you can see that omega by Vp1 on both sides will cancel. So, what you get here is sin theta I equals sin theta r, and because your theta I and theta r are between 0 to pi by 2, you are looking at two quantities whose signs are equal and the angles are between 0 to pi by 2. The only condition that will be valid is when theta r equals theta I. So, this is your first Snell's law, correct. First Snell's law, which says that angle of reflection is equal to angle of incidence. To get the second law, you equate the first ki sin theta I to the last term kt sin theta t. So, you get omega by Vp1 sin theta I must be equal to omega by Vp2 sin theta t. Omega cancels on both sides. Since the phase velocity in region 1 is the velocity of light divided by square root of epsilon r1, and velocity in region 2 is c by square root epsilon r2, and recognizing that square root epsilon r1 is actually the refractive index n1. This is the refractive index n1, this epsilon r2 is the refractive index n2. What you get here is sin theta I, which is n1, is equal to n2 sin theta t. So, if you know your boundary conditions, you do not have to remember what is Snell's law, you can derive Snell's law from this. Okay. So, this is the second Snell's law in fact. So, this law gives you the angle of incidence to angle of refraction or the transmission. Okay. Now, let us look at, the problem is not yet done, we have only applied one boundary condition, we need to apply a second boundary condition. The second boundary condition is in terms of H fields, right. So, what was the boundary condition? You had to find out what are the tangential components of the H, which were minus x hat cos theta I, x hat cos theta I minus x hat cos theta t. So, I need to hopefully remember this correctly. So, I will go back and write this. So, the total tangential component in the first medium is minus cos theta I E I by eta 1 plus cos theta r E r by eta 1, which must be equal to minus cos theta t E t by eta 2. Eta 1 and eta 2 are the impedances of the medium in region 1 and region 2. So, if I have not written it earlier, this should be equal to square root of mu by epsilon. Okay. Now, you have two equations. One equation says that E I plus E r is equal to E t. The second boundary condition is given by this equation, correct. Now, you might ask what happened to the phase factors? Well, phase factors were all equal to each other, right. Phase factors were equal because this condition was to be true, and because of this condition only we got two Snell's law, one Snell's law and another Snell's law. So, we do not have to worry about the phase factors for second component, that is for the magnetic field component. Now, I will leave this as a very simple exercise for you to simplify the equations and obtain the reflection coefficient, which is the ratio of reflected electric field amplitude to the incident electric field amplitude for the TE case that we have considered, and this turns out to be eta 2 cos theta I minus eta 1 cos theta t divided by eta 2 cos theta I plus eta 1 cos theta t. This equation, this is valid for the TE case, okay, is the reflection coefficient that we wanted to derive. This relates the ratio of the electric field in the reflected to the incident electric field. Similarly, you can find out what is the transmission coefficient for the TE case, which would be the ratio of ET to EI, and this will be equal to 2 eta 2 cos theta I divided by eta 2 cos theta I plus eta 1 cos theta t. Okay. So, this would be the transmission coefficient. Now, if you were to consider two situations and start varying the angle of incidence, okay, first let me consider a situation where magnitude of the reflection coefficient that I am going to plot, I will consider two situations. Okay. One situation I will assume that the medium has a refractive index N1 is less than N2. Okay. This for example could be 1 and N2 could be 1.44, okay, which is silica for us. Okay. Then we will interchange the first medium as N2 and the medium as N1. Okay. So, this would be N1 equals 1.44 and N2 equals 1 for the second case. In this case obviously N1 is greater than N2. Your impedance eta is given by square root of mu by epsilon, but this can be written as mu 0 by epsilon 0 epsilon r, and this further can be simplified by denoting the square root of mu 0 by epsilon 0 as eta 0. Okay. So, you get eta 0 divided by square root of epsilon r, or this is equal to impedance in the free space divided by refractive index n. So, what I want to say is that given a medium having a relative permittivity epsilon r, the impedance is inversely proportional to the square root of epsilon r, or equivalently 1 by n, where n is the refractive index. So, higher the refractive index, lower the medium characteristic impedance eta. Okay. Now, consider first the case where N1 is less than N2. So, your wave is happily coming from air and it goes into silica. Okay. What will happen here is that the transmission, the reflection coefficient keeps on increasing slowly at some point, which is at theta I equal to 0, and maximum you can get is 90 degrees, because that is where you get what is called as the grazing angle. So, as it goes slowly and eventually reaches up 1. Okay. So, it asymptotically reaches up to 1 at theta equal to 90 degrees. This is a phenomenon that you might be familiar. So, you can actually see like this, if a ray of light falls perpendicularly, I mean normally to the interface, it will be reflected back in the same direction. However, when the wave comes and hits the surface this way, the wave also gets parallelly transmitted. It is kind of a transmission along the axis. Okay. This is called as grazing angle incidence and transmission from the grazing angle, and this is valid actually for both TE as well as TM waves. Okay. So that is why at 90 degrees the reflection coefficient goes to 1, that is almost entire wave basically gets reflected. You can try this. If you were to take a book and then hold it up and then you try to read, you will get maximum reflection because light is getting reflected. If there is anything that is printed on the piece of paper, you will not be able to read it. So this grazing angle is something that is common to TE and TM. Let us switch the cases now. I consider N1 equals 1.44, N2 equals 1. What happens in this case is that at theta I equal to 0, it begins in the same way, okay, and thereafter it kind of goes and then suddenly goes to, actually there is a small decrease actually which I should point out here. So hold on a minute. So this is your case when N1 is less than N2. Okay. Now for the case where N1 is greater than N2, you will see that this would go like this and suddenly hit reflection coefficient equal to 1. But what happens is that there is a sudden change in the reflection coefficient. This occurs at an angle which we conveniently call as critical angle. Okay. What is this critical angle? This critical angle is the angle at which the reflection coefficient becomes equal to 1, which means that whatever the light that is incident after this theta c will be entirely reflected back. This happens only when N1 is greater than N2, that is the medium has of the first, the incident medium has a higher refractive index compared to the second medium which is of a lower refractive index, that is going from denser to rarer medium. This phenomenon when N1 is greater than N2, there is a certain angle called as critical angle is called as total internal reflection. Okay. This is called as total internal reflection, and what happens in this total internal reflection is that if this is the boundary that we are considering, okay, and this was the normal that we had, remember this was one of the axes that we had, as the wave is incident from a medium of higher refractive index N1 greater than N2, this is N2, okay, this wave gets reflected totally. So this angle must exceed, the incidence angle must exceed the critical angle as you have measured. Okay. While this is a simpler picture, the electric field amplitudes would not go away. What would happen is there would be propagation of the electric field along the axis. Okay. However, this amplitude of the electric field decays as you go away from the interface from the top to bottom. You will see that the electric field amplitude starts to decay along this way. However, it continues to kind of propagate parallelly. Okay. It decays in amplitude as you go away from the surface, but it will be directed, it will be propagating along the x axis, okay, or along the surface of the boundary. Such a phenomenon is called as such a wave is called as evanescent wave. Okay. Evanescent waves do not carry any power. Okay. You can show by calculating the electric field and magnetic field that electric field and magnetic field will be 90 degree out of phase with each other, and therefore they carry no power. However, the amplitude of the electric field will decay. Okay. The rate at which this decays depends on what is the difference between N1 and N2. If the difference is large, then it will decay faster. If the difference is small, then it will decay at a lesser way. So this is the evanescent wave whose amplitude is all decreasing, and eventually the amplitude will be equal to, very nearly equal to 0. So you can imagine waves along the ocean which are propagating. This phenomenon is called as total internal reflection. We will talk about modes of optical fiber by talking initially about total internal reflection in the next module. Thank you very much.